In mathematics, the limit inferior and limit superior of a sequence can be thought of as limiting bounds on the sequence. They can be thought of in a similar fashion for a function. For a set, they are the infimum and supremum of the set's limit points, respectively. In general, when there are multiple objects around which a sequence, function, or set accumulates, the inferior and superior limits extract the smallest and largest of them. The type of object and the measure of size is context-dependent, but the notion of extreme limits is invariant. Limit inferior is also called infimum limit, liminf, inferior limit, lower limit, or inner limit. Limit superior is also known as supremum limit, limit supremum, limsup, superior limit, upper limit, or outer limit. Definition for sequences: the limit inferior of a sequence is defined by or. Similarly, the limit superior of is defined by or. Alternatively, the notations and are sometimes used. If the terms in the sequence are real numbers, the limit superior and limit inferior always exist, as real numbers or a plus or minus a. More generally, these definitions make sense in any partially ordered set, provided the suprema and infima exist, such as in a complete lattice. Whenever the ordinary limit exists, the limit inferior and limit superior are both equal to it. Therefore, each can be considered a generalization of the ordinary limit, which is primarily interesting in cases where the limit does not exist. Whenever liminf xn and limsup xn both exist, we have limits inferior-superior are related to big O notation in that they bound a sequence only in the limit. The sequence may exceed the bound. However, with big O notation the sequence can only exceed the bound in a finite prefix of the sequence, whereas the limit superior of a sequence like an may actually be less than all elements of the sequence. The only promise made is that some tail of the sequence can be bounded by the limit superior plus an arbitrarily small positive constant. The limit superior and limit inferior of a sequence are a special case of those of a function. The case of sequences of real numbers, in mathematical analysis, limit superior and limit inferior are important tools for studying sequences of real numbers. Since the supremum and infimum of an unbounded set of real numbers may not exist, it is convenient to consider sequences in the affinely extended real number system. We add the positive and negative infinities to the real line to give the complete totally ordered set, which is a complete lattice. Interpretation equals, consider a sequence consisting of real numbers. Assume that the limit superior and limit inferior are real numbers. The limit superior of is the smallest real number such that, for any positive real number, there exists a natural number such that for all. In other words, any number larger than the limit superior is an eventual upper bound for the sequence. Only a finite number of elements of the sequence are greater than. The limit inferior of is the largest real number that, for any positive real number, there exists a natural number such that for all. In other words, any number below the limit inferior is an eventual lower bound for the sequence. Only a finite number of elements of the sequence are less than. Properties equals, the relationship of limit inferior and limit superior for sequences of real numbers is as follows. As mentioned earlier, it is convenient to extend to a. Then, in a converges if and only if. In which case is equal to their common value. Since the limit inferior is at most the limit superior, the condition. And the condition. If and, then the interval, S, need not contain any of the numbers xn, but every slight enlargement, I micron, S plus I micron will contain xn for all but finitely many indices n. In fact, the interval, S, is the smallest closed interval with this property. We can formalize this property like this: there exist subsequences and if for which we have. On the other hand, there exists a so that for all. To recapitulate, if is greater than the limit superior, there are at most finitely many greater than. If it is less, there are infinitely many. If is less than the limit inferior, there are at most finitely many less than. If it is greater, there are infinitely many. In general we have that the liminf and limsup of a sequence are respectively the smallest and greatest cluster points. For any two sequences of real numbers, the limit superior satisfies subadditivity whenever the right side of the inequality is defined. Analogously, the limit inferior satisfies superadditivity. In the particular case that one of the sequences actually converges, say, then the inequalities above become equalities. Examples: as an example, consider the sequence given by xn equals sin, n. Using the fact that pi is irrational, one can show that and this is because the sequence 1, 2, 3 is equidistributed mod 2 euro, a consequence of the equidistribution theorem. An example from number theory is where Pn is the nth prime number. The value of this limit inferior is conjectured to be 2 euro. This is the twin prime conjecture euro, but as of April 2014 has only been proven to be less than or equal to 246. The corresponding limit superior is, because there are arbitrary gaps between consecutive primes. Real-valued functions assume that a function is defined from a subset of the real numbers to the real numbers. As in the case for sequences, the limit inferior and limit superior are always well defined if we allow the values plus a and aa. In fact, if both agree, then the limit exists and is equal to their common value. For example, given f, x, equals sin, 1/x, we have lim supxa0f, x, equals 1 and lim infxa0f, x, equals a 1. The difference between the two is a rough measure of how wildly the function oscillates, and in observation of this fact, it is called the oscillation of f at a. This idea of oscillation is sufficient to, for example, characterize Riemann integrable functions as continuous except on a set of measures 0, 1. Note that points of non-zero oscillation are discontinuities which, unless they make up a set of 0, are confined to a negligible set. Functions from metric spaces to metric spaces. There is a notion of limsup and liminf for functions defined on a metric space whose relationship to limits of real-valued functions mirrors that of the relation between the limsup, liminf, and the limit of a real sequence. Take metric spaces x and y, a subspace E contained in x, and a function f, e or y. The space y should also be an ordered set, so that the notions of supremum and infimum make sense. Define, for any limit point a of E, and where b, a, I micron denotes the metric ball of radius I micron about a. Note that as I micron shrinks, the supremum of the function over the ball is monotone decreasing, so we have. And similarly, this finally motivates the definitions for general topological spaces. Take x, y, e and a as before, but now let x and y both be topological spaces. In this case, we replace metric balls with neighborhoods. There is a way to write the formula using a lim using nets and the neighborhood filter. This version is often useful in discussions of semi-continuity which crop up in analysis quite often. An interesting note is that this version subsumes the sequential version by considering sequences as functions from the natural numbers as a topological subspace of the extended real line, into the spaces NAA. Sequences of sets. The power setter, x, of a set X is a complete lattice that is ordered by set inclusion, and so the supremum and infimum of any set of subsets always exist. In particular, every subset Y of X is bounded above by X and below by the empty set A because of #Y#X. Hence, it is possible to consider superior and inferior limits of sequences in a X. There are two common ways to define the limit of sequences of sets. In both cases, the sequence accumulates around sets of points rather than single points themselves. That is, because each element of the sequence is itself a set, there exist accumulation sets that are somehow nearby to infinitely many elements of the sequence. The supremum outer limit is a set that joins these accumulation sets together. That is, it is the union of all of the accumulation sets. When ordering by set inclusion, the supremum limit is the least upper bound on the set of accumulation points because it contains each of them. Hence, it is the supremum of the limit points. The infimum inner limit is a set where all of these accumulation sets meet. That is, it is the intersection of all of the accumulation sets. When ordering by set inclusion, the infimum limit is the greatest lower bound on the set of accumulation points because it is contained in each of them. Hence, it is the infimum of the limit points. Because ordering is by set inclusion, then the outer limit will always contain the inner limit. Hence, when considering the convergence of a sequence of sets, it generally suffices to consider the convergence of the outer limit of that sequence. The difference between the two definitions involves how the topology is defined. In fact, the second definition is identical to the first when the discrete metric is used to induce the topology on X. Equals general set convergence equals, in this case, a sequence of sets approaches a limiting set when the elements of each member of the sequence approach the elements of the limiting set. In particular, if Xn is a sequence of subsets of X, then, limsup Xn, which is also called the outer limit, consists of those elements which are limits of points in Xn taken from infinitely many n. That is, Xa limsup Xn if and only if there exists a sequence of points xk and a subsequent xnk of Xn such that xk xnk and xkax is kaa, liminf Xn, which is also called the inner limit, consists of those elements which are limits of points in Xn for all but finitely many n. That is, Xa liminf Xn if and only if there exists a sequence of points xk such that xk and xkax is kaa. The limit lim Xn exists if and only if liminf Xn and limsup Xn agree, in which case lim Xn equals limsup Xn equals liminf Xn. Equals special case, discrete metric equals, this is the definition used in measure theory and probability. Further discussion and examples from the set theoretic point of view, as opposed to the topological point of view discussed below, are at set theoretic limit. By this definition, a sequence of sets approaches a limiting set when the limiting set includes elements which are in all except finitely many sets of the sequence and does not include elements which are in all except finitely many complements of sets of the sequence. That is, this case specializes the general definition when the topology on set X is induced from the discrete metric. Specifically, for points X are X and Y are X, the discrete metric is defined by under which a sequence of points xk converges to point X or X if and only if xk equals X for all except finitely many k. Therefore, if the limit set exists it contains the points and only the points which are in all except finitely many of the sets of the sequence. Since convergence in the discrete metric is the strictest form of convergence, this definition of a limit set is the strictest possible. If Xn is a sequence of subsets of X, then the following always exist. Limsup Xn consists of elements of X which belong to Xn for infinitely many n. That is, Xa limsup Xn if and only if there exists a subsequence xnk of Xn such that xnk for all k, liminf Xn consists of elements of X which belong to Xn for all except finitely many n. That is, Xa liminf Xn if and only if there exists some m greater than 0 such that xn for all n, m. Observe that Xa limsup Xn if and only if Xa permil liminf Xn c. The lim Xn exists if and only if liminf Xn and limsup Xn agree, in which case lim Xn equals limsup Xn equals liminf Xn. In this sense, the sequence has a limit so long as every point in X either appears in all except finitely many Xn or appears in all except finitely many Xn c. Using the standard parlance of set theory, set inclusion provides a partial ordering on the collection of all subsets of X that allows set intersection to generate a greatest lower bound and set union to generate a least upper bound. Thus, the infimum or meet of a collection of subsets is the greatest lower bound while the supremum or join is the least upper bound. In this context, the inner limit, liminf Xn, is the largest meeting of tails of the sequence, and the outer limit, limsup Xn, is the smallest joining of tails of the sequence. The following makes this precise. Let n be the meet of the nth tail of the sequence. That is, the sequence n is non-decreasing because each n plus 1 is the intersection of fewer sets than n. The least upper bound on this sequence of meets of tails is. So the limit infimum contains all subsets which are lower bounds for all except finitely many sets of the sequence. Similarly, Let Jn be the join of the nth tail of the sequence. That is, the sequence Jn is non-increasing because each Jn plus 1 is the union of fewer sets than Jn. The greatest lower bound on this sequence of joins of tails is. So the limit supremum is contained in all subsets which are upper bounds for all except finitely many sets of the sequence. Examples the following are several set convergence examples. They have been broken into sections with respect to the metric used to induce the topology on set X. Using the discrete metric, the Boolean-Cantelli lemma is an example application of these constructs. Using either the discrete metric or the Euclidean metric, consider the set X equals 0, 1 and the sequence of subsets. The odd and even elements of the sequence form two subsequences, 0, 0, 0, and 1, 1, 1, which have limit points 0 and 1, respectively, and so the outer or superior limit is the set 0, one of these 2 points. However, there are no limit points that can be taken from the Xn sequence as a whole, and so the interior or inferior limit is the empty set. That is, limsup Xn equals 0, 1, liminf Xn equals. However, for n equals 0, 0, 0, and Zn equals 1, 1, 1, limsup n equals liminf n equals limin equals 0, limsup Zn equals liminf Zn equals lim Zn equals 1. Consider the set X equals 50, 20, minus 100, minus 25, 0, 1 and the sequence of subsets. As in the previous two examples, limsup Xn equals 0, 1, liminf Xn equals. That is, the four elements that do not match the pattern do not affect the liminf and limsup because there are only finitely many of them. In fact, these elements could be placed anywhere in the sequence. So long as the tails of the sequence are maintained, the outer and inner limits will be unchanged. The related concepts of essential inner and outer limits, which use the essential supremum and essential infimum, provide an important modification that squashes countably many interstitial additions. Using the Euclidean metric, consider the sequence of subsets of rational numbers. The odd and even elements of the sequence form two subsequences, 0, 13, 3/4, and 1, 13, 1/4, which have limit points 1 and 0, respectively, and so the outer or superior limit is the set 0, one of these 2 points. However, there are no limit points that can be taken from the Xn sequence as a whole, and so the interior or inferior limit is the empty set. So, as in the previous example, limsup Xn equals 0, 1, liminf Xn equals. However, for n equals 0, 13, 3/4, and Zn equals 1, 13, 1/4, limsup n equals liminf n equals limin equals 1, limsup Zn equals liminf Zn equals lim Zn equals 0. In each of these four cases, the elements of the limiting sets are not elements of any of the sets from the original sequence. The I-copyright limit of a solution to a dynamic system is the outer limit of solution trajectories of the system. Because trajectories become closer and closer to this limit set, the tails of these trajectories converge to the limit set. For example, an LTI system that is the cascade connection of several stable systems with an undamped second-order LTI system will oscillate endlessly after being perturbed. Hence, if the position and velocity of the system are plotted against each other, trajectories will approach a circle in the state space. This circle, which is the I-copyright limit set of the system, is the outer limit of solution trajectories of the system. The circle represents the locus of a trajectory corresponding to a pure sinusoidal tone output. That is, the system output approximates a pure tone. Generalized definitions. The above definitions are inadequate for many technical applications. In fact, the definitions above are specializations of the following definitions. Definition for a set equals, the limit inferior of a set X-Y is the infimum of all of the limit points of the set. That is. Similarly, the limit superior of a set X is the supremum of all of the limit points of the set. That is. Note that the set X needs to be defined as a subset of the partially ordered set Y that is also a topological space in order for these definitions to make sense. Moreover, it has to be a complete lattice so that the suprema and infima always exist. In that case every set has a limit superior and a limit inferior. Also note that the limit inferior and the limit superior of a set do not have to be elements of the set. Equals definition for filter bases equals, take a topological space X and a filter base B in that space. The set of all cluster points for that filter base is given by. Where is the closure of? This is clearly a closed set and is similar to the set of limit points of a set. Assume that X is also a partially ordered set. The limit superior of the filter base B is defined as when that supremum exists. When X has a total order, is a complete lattice and has the order topology. Proof: similarly, the limit inferior of the filter base B is defined as when that infimum exists. If X is totally ordered, is a complete lattice, and has the order topology, then if the limit inferior and limit superior agree, then there must be exactly one cluster point and the limit of the filter base is equal to this unique cluster point. Specialization for sequences and nets. Note that filter bases are generalizations of nets, which are generalizations of sequences. Therefore, these definitions give the limit inferior and limit superior of any net as well. For example, take topological space and a net, where is a directed set and for all. The filter base generated by this net is defined by. Therefore, the limit inferior and limit superior of the net are equal to the limit superior and limit inferior of respectively. Similarly, for topological space, take the sequence where for any with being the set of natural numbers. The filter base generated by this sequence is defined by. Therefore, the limit inferior and limit superior of the sequence are equal to the limit superior and limit inferior of respectively. See also, essential supremum and essential infimum, envelope, one-sided limit, Ni derivatives, set theoretic limit. References. External links, Haswinkel, Michiel, ed., Upper and Lower Limits, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4.